Hi, hello dear students. Welcome to physics class of PU2. In the previous class discussion, I have given you the introduction about the syllabus. What are the different topics we have to study in physics in part 1 as well as in part 2. Now in this video class, I am going to start here the new chapter, chapter number 12, atoms from part 2. You all are familiar with the name atoms. In this topic, we have to make an entry into the mysterious world of atomic physics through the study of the atoms having only one electron in their outermost orbit. In this topic, we have to discuss about the different atomic models proposed by the different scientists to explain about the atomic structure. The existence of atoms has been proposed since the time of early Indian and Greek philosophers around 400 BC. According to the view of Greek philosophers, the atoms are the fundamental building blocks of matter. So, what is an atom? According to them, the atoms are what? The building blocks of matter. The word atom is derived from the Greek word which means uncuttable or non-divisible, which is derived from the Greek word atomio, which means what? Uncuttable or non-divisible. If we look at into the history of the atom, in 1805, John Dalton proposed an atomic theory. According to him, the matter consists of what? The indivisible atoms. So the same thing he also proposed as given by the Greek philosophers. He also told what? All matters all matter is composed of what? Small particles called as atoms, which are indivisible, right? And also he told that all the atoms of a given element have identical properties and identical mass, right? All the oxygen atoms have same mass and same properties, but the atoms of different elements have different mass. For example, oxygen atom is different mass and nitrogen atom is having different mass. And the compounds are formed when the different atoms are combined in a definite ratio. When compounds are formed from the atoms of different elements, they combine in the fixed ratio. And also he told that a chemical reactions involves the rearrangement of atoms only. There is no creation of atoms or destroy of atoms takes place. Only there is a rearrangement of atoms takes place in a chemical reactions. So what are the important merits of this theory is this Dalton's atomic theory explains about what? The law of conservation of mass. So during the chemical reactions, only there is a rearrangement of atoms takes place. So there is a neither atoms are neither created nor be destroyed at the chemical reaction, right? Therefore, it explains about the law of conservation of mass. It explains about a law of constant composition, and also it explains about the law of multiple proportion. But this theory fails to explain about what? The subatomic particles, right? So later on what happens, the experimental later on at the end of the 19th century or the beginning of the 20th century, the different experiments are conducted by different scientists, and they have established that what? The atoms can be further divided into subatomic particles. So at the we have certain experiments are conducted at the end of 19th century and at the beginning of 20th century by different scientists. They have established what here? The atoms can be further divided into subatomic particles. These are what? The electrons, protons and neutrons, right? So we can divide an atom into subatomic particles, which are those electrons, protons and neutrons. The experiments related to this, the discovery of subatomic particles, already you have discussed in PU1 chemistry topic atomic structure. In detail you have discussed about these discovery of subatomic particle experiments, right? So here we have given here the table which gives the subatomic particles with their charge values. What is the charge of an electron? Charge of an electron is negative, charge of the proton is positive, neutron is electrically neutral, right? And the magnitude of charge of electron is 1.6 into 10 to the power minus 19 coulomb, so it is negative. The charge of the proton is equal in magnitude that of the electron, but it is positive. And also in this table I have given here the masses of the subatomic particle in terms of kg as well as in terms of AMU, that is atomic mass unit. You can refer this table. Now the observations obtained from the different experiments, those explains what here. As you know that now the atoms are composed of what? The subatomic particles which are carrying a charge of positive and negative. So after knowing this, the subatomic particles with their charges, after this the different atomic models were proposed to explain the distribution of these charged particles in an atom. So how these charged particles are subatomic particles are distributed in an atom. So to explain this, the different atomic models were proposed. So here we have to discuss what is an atomic model and what is an atomic model and the different atomic models proposed by different scientists to explain the structure of atom, right? So first thing here, what is an atomic model? An atomic model is one which can describe an atom and which can explain the properties of an atom successfully. That is called as what? An atomic model. An atomic model is one which can describe an atom completely and which can explain all the properties of an atom successfully. That is called as what? An atomic model. Any atomic model proposed should explain satisfactorily three important points. One is what? The electrical neutrality of the atom, the stability of the atom, and the origin of spectral lines. So what is electrical neutrality of the atom? That means what? Neutrality means what? The number of the atom should have what? The equal number of protons and electrons. That is called as what? The neutrality of the atom. And also it should explain satisfactorily about the about the stability of the atom, and also it should explain the origin of spectral line. Now let us discuss here the important atomic models proposed to explain the structure of atom. Now let us see whether all these models explain about these 3 points successfully or not. The first atomic model was proposed by J.J. Thomson. After his discovery of electron in 1897, the many atomic models were proposed by different scientists to explain the structure of the atom. So who discovered an electron? J.J. Thomson discovered an electron in 1897. So J.J. Thomson proposed the first atomic model. After this, the many atomic models were proposed by different scientists to explain the structure of atom. Which are those? The first one is Thomson's atomic model, and second one is the Rutherford atomic model. The Rutherford atomic model is also called as the nuclear atomic model because in 1909 Rutherford discovered the nucleus by his alpha particle scattering experiment. Then we have the Rutherford atomic model. After this we have Bose atomic model, right? Bose atomic model is proposed to overcome the demerits of the Rutherford atomic model. Then we have Sommerfeld's atomic model and vector atomic model. So these two last, these Sommerfeld's atomic model and vector atomic models are what? These two are quantum mechanical models. Now in this chapter we are going to discuss about the Thompson's atomic model, Rutherford atomic model and Bohr's atomic model, right? Now let us discuss here the first one, the Thompson's atomic model. So according to the J.J. Thomson atomic model, according to him, the positive charge of the atom is uniformly distributed in a sphere of diameter about what? 10 to the power minus 10 meter. That is about 1 angstrom. 10 to the power minus 10 meter what? 1 angstrom. So according to the J.J. Thomson model, the positive charge of the atom is uniformly distributed. It is uniformly distributed in a sphere of diameter about 10 to the power minus 10 meter. And the negatively charged electrons are embedded in it like acids in a watermelon. So this model is also called as, Thomson's atomic model is also called as watermelon model, because these seeds are nothing but what here? The electrons in a watermelon like structure we are explaining. It is also called as what? Watermelon model. We are comparing what here? The atom into what? Watermelon according to J.J. Thomson. Alright. So the seeds are nothing but what? The electrons, and that reddish color is nothing but what? The positive charge. Right. According to him, the positive charge of the atom is uniformly distributed in a sphere of diameter about 10 to the power minus 10 meter. So it is uniformly distributed throughout the volume of the atom according to J.J. Thomson, and the electrons are embedded in it like a seeds in a watermelon. Right. So it is also called as what? Watermelon model. So simple thing is what here? According to him, the positive charge of the atom is uniformly distributed throughout the volume of the atom, and the negatively charged electrons are embedded in it like acids in a watermelon. So this model is also called as what here? Plum pudding model. So Thomson believed that what? The electrons are like a plums. Plums means what? The fruits like dried grapes. Those are called as what? The plums, right? These plums are embedded in a positively charged pudding. So that's why it is also called as plum pudding model. This model is also called as what? Plum pudding model, because the electrons are embedded like plums in a pudding, right? Plums means what? The plums means the fruits like dried grapes. Those are called as what? The plums, right? So those are embedded in a pudding. So this is called as what? The plum pudding model. So here in the figure you can refer here plum pudding model structure, watermelon model structure we can compare here. So according to J.J. Thomson, what we can conclude here from the J.J. Thomson atomic model, it explains about the neutrality of the atom, right? The positive charge is equal to the negative charge, but it could not explain about what? The stability and the emission of spectral lines, right? And what happens later on? The Rutherford, he is a student of J.J. Thomson. He proved that the positive charge is not uniformly distributed in a sphere, right? The positive charge is not uniformly distributed in a sphere. Positive charge is not distributed in a sphere as suggested by J.J. Thomson. So, right? According to Rutherford, the positive charge of the atom is concentrated in a very small region at the center of the atom, that is called as the nucleus, right? And the electrons are revolve around the nucleus. So according to Rutherford, he is a student of J.J. Thomson. He conducted the experiment to explain these results. So he conducted an experiment called as what? The alpha particle experiment, alpha particle scattering experiment by a thin gold foil he conducted, and he proposed that what? The, as suggested by a J.J. Thomson, the positive charge of the atom is not uniformly distributed in a sphere, and that positive charge of the atom is concentrated only in a very small region at the center of the atom called as the nucleus, and those electrons are revolve around the nucleus. So this is what the proposed by what Rutherford atomic model. So according to the Rutherford proposed the what the second atomic model, based on what Rutherford proposed what the second atomic model to explain the structure of the atom based on his alpha particle scattering experiment by thin gold foils. Now let us discuss here the alpha particle scattering experiment by a thin gold foils as conducted by Rutherford and Giger and Marsden. Rutherford and along with the Giger and Marsden this experiment is conducted. So that's why it is also called as Rutherford alpha particle scattering experiment by a thin gold foil. It is also called as what Giger Marsden experiment. So along with the Rutherford, these two scientists are also involved in this involved in the performing this experiment. So that this experiment is also called as what the Giger Marsden experiment. Now let us discuss this the Giger-Marsden experiment or Rutherford alpha particle scattering experiment in detail. Let us see the experimental setup. What are the observations made by from this experiment, and what are the conclusions taken from this experiment to explain the atomic structure, right? So as I told you now, the Rutherford along with the Giger and Marsden performed a series of experiments on the scattering of alpha particles due to atoms of thin gold foils. So you should know here what is meant by alpha particle. So first point, you have to understood here what is an alpha particle. An alpha particle is a helium atom from which two electrons have been removed, right? So the alpha particle is nothing but a helium nucleus, right? So we all know that the atomic number of helium is 2 and its mass number is 4. So when two electrons are removed from the helium atom, so we have only a helium nucleus with two protons and two neutrons, so that the protons are having the positive charge and the neutrons are electrically neutral, so that the charge of the alpha particle is what the plus 2e, right? If two electrons have been removed uh, from the helium atom, so only we have remain with what the helium nucleus, its charge is plus 2e and mass is what the 4 times of the mass of the proton. So we have only two protons and two neutrons remaining in helium nucleus, and its mass is what 4 times of the mass of the proton. So why we take the 4 times of proton? Because the mass of proton is nearly equal to the mass of neutron. So helium the alpha particle is nothing but a helium nucleus. The charge of an alpha particle is plus 2e. So charge of the alpha particle is plus, right? And it is denoted by the symbol He plus 2. Now with this, what is an alpha particle? Let us start here the description of the experimental setup. The basic experimental arrangement used by the Rutherford and his associates, which are the Giger and Marsden, as shown in the figure here. So what are the important apparatus used in the experimental arrangement? So the first one, we have the lead block here, right? So lead block, inside the lead block we have a radioactive source which gives the alpha particle. So we have kept inside the lead block a radioactive element is placed. That radioactive element gives the alpha particles due to radioactivity phenomena. So first one, we have the lead block. In lead block we have a radioactive element which is a source of alpha particle, right? So the radioactive element gives the alpha particles. So the second one here is what the collimator. So why the collimator is used? The collimator gives the narrow beam of alpha particles. To get the narrow beam of alpha particles, we have used here in the experimental arrangement there is an collimator. So collimator which gives a beam of alpha particle, narrow beam of alpha particle. Then we have a gold foil here, a thin gold foil, right? The thickness of the gold foil is about 10 to the power minus 8 meter. So the gold foil is the target, right? And the thickness of the gold foil is 10 to the power minus 8 meter, right? So first one is the lead block, and the second one is the collimeter, and the third one is gold foil about the thickness 10 to the power minus 8 meter. So in another figure I have shown here, this is the lead block, right? So we have a narrow beam of alpha particles here, then we have the gold foil. Then one more arrangement is what? The circular screen. We have a circular screen here. This is a circular screen which is coated with what? The zinc sulfide, right? ZNS. So this is a ZNS screen. That means what? We have a circular screen on which the zinc sulfide is coated, right? Zinc sulfide is coated, so which is a screen, circular screen. Now why here the zinc sulfide is coated on the circular screen? Because which acts as a fluorescent screen, that means what? Any particle hits the screen, a flashlight is observed, right? To see the scattering of alpha particles through the gold foil, the circular screen is used with the quotation of what? ZNS. So which acts as a what? The flashlight. So any particle hits the screen, the flashlight is obtained. So that's why the fluorescent screen is used there. And one more is what? The detector or the movable detector. It is a movable detector, and it is also called as what? The microscope. So this detector can we move from this position to this position, so that's why it is called as the movable detector. So in this way, circular screen, as the circular screen we have, in the same path we can move this detector, that is microscope. So now we have discussed here about what? The experimental setup and with apparatus. So the first one here, what? The lead block. In lead block we have placed a radioactive element which produces the alpha particles. Second one, a collimeter which gives a narrow beam of alpha particles. Then we have the gold foil about the thickness 10 to the power minus 8 meter. Then we have this fluorescent circular screen. Fluorescent means any particle hits, it gives the flashlight. Then we have the movable detector here. This detector acts as a microscope, so any after we can see the scattered alpha particles from this movable detector. So this is what the experimental setup used by the Rutherford and his associates, right? So the experimental setup consists of what? A narrow beam of alpha particles from the radioactive source, which are incident on a circular screen coated with the zinc sulfide after passing through the gold foil, right? And these alpha particles are scattered in different direction, and these scattered alpha particles are observed with the help of movable detector. So this is an experimental setup and how it works. Once again I will explain the arrangement here, then we will discuss about the observations and conclusions of this experiment. A narrow beam of alpha particles which falls on a thin gold foil of thickness about 10 to the power minus 8 meter. A narrow beam of alpha particles which falls on what? Thin gold foil of thickness 10 to the power minus 8 meter. After passing through this thin gold foil, those alpha particles falls on what? A fluorescent screen. So after passing through the thin gold foil, these alpha particles falls on what? This fluorescent screen, and these scattered alpha particles are observed with the help of movable detector, right? So movable detector is used to observe the scattered particle with a scattering angle theta. So one more point you have to remember here, the scattering angle, right? What is a scattering angle? You have to remember, scattering angle means what? The angle theta the angle theta of the deviation of the alpha particle from the original direction. So about which angle those alpha particle are scattered from the initial direction, that is called as what? The angle of scattering, or it is also called as what? The scattering angle. The deviation of an alpha particle, the deviation of an alpha particle from the original direction after scattering through the gold foil, that is called as the scattering angle theta. So with all these discussion regarding the experimental setup of the Giger-Marsden experiment or Rutherford alpha particle scattering experiment, now let us see what are the observations made by the Rutherford with his experiment. Now let us discuss here the observations one by one. Right. Now the first observation what he made is the most of the alpha particle passed through the gold foil undeflected. Right, the most of the alpha particles are passed through the gold foil. The most of the alpha particles are passed through the gold foil undeflected. Undeflected means what? Here they pass straight through the foil without suffering any deviation. Right, you can see here after passing through the gold foil, right, without any deviation they pass straight through the foil. That is the first observation. Right, the most of the alpha particles pass through the gold foil with undeflection, right, without any deviation. They pass straight to the foil without suffering any deviation. So what is the reason for this we will discuss. So let us first see the important observation. Right, the most of the alpha particles pass through the gold foil and deflection, the first one. So in this figure we can see here the first A, the rays shown by the symbol A are what? The alpha particles which are passed with undeflection. So here these rays are called as what? These rays are passed without any deviation. Right, next one, only about 0.14%, only about 0.14% of the alpha particles scatter at an angle greater than 1 degree. Right, you can see here the B. Right, at the experiment symbol B represents what here? So when these alpha particles hits this ZNS screen or fluorescent screen, the flashlight is observed here. Right, in this way it is observed. Right, so here these rays are what? They pass without any deviation. Only about 0.14% of the alpha particles are scattered at an angle greater than the 1 degree. Scattering angle is greater than 1 degree. So these rays are shown here. Right, B. Now a very small number of alpha particles, a very small number of alpha particles, about 1 in 8,000, 1 in 8,000 deflected by more than 90 degree, which is deflected by more than 90 degree, or even it retraces its original path, that is the angle of deflection was 180 degree. That means the alpha particle after scattering which retraces its original path, that means what? The angle of scattering is 180 degree. Right, so what are the important observations observed by the Rutherford? We have to give the reason for this. That is what the conclusion, conclusion of the Rutherford alpha particle scattering experiment. So most of the alpha particles passed through the gold foil with undeflection. Some of the alpha particles were deflected through a small angle that is greater than 1 degree, and very a small number of alpha particles, about 1 in 8,000, 1 in 8,000, which practically retraces its original path. That means the angle of deflection for those particles is 180 degree. So with all these observations, here you can here we can refer the graph of number of alpha particles against the angle of scattering. So this graph shows what here? The graph of the number of alpha particles scattered n versus the angle of scattering theta. Right, so now from this graph what we can get the information is, if you refer this area of the graph, the only a few number of alpha particles, only a few number of alpha particles are scattered or deflected with an angle greater than 90 degree and deflected with 180 degree, right? But a large number of alpha particles which are passed through the gold foil with undeflection, or the angle of scattering is very very small. So with all these observations, we can give the reason for the observations, and those are the conclusions of what Rutherford alpha particle scattering experiment or Giger Marsden alpha particle scattering experiment. Now let us see the conclusions of the experiment with all those observations. Right? Let us give the reason for the what the observations. So the first one is, as most of the alpha particles pass through the gold foil with undeflection, it indicates what the most of the space in an atom is empty, right? The reason for the the alpha particle which pass through the gold foil with undeflection is what it indicates, what the most of the space in an atom is empty, right? The most of the space in an atom is empty. This is the first conclusion. The second one, so the alpha particles are what, as you know that the alpha particle is nothing but helium nucleus, its charge is +2. So alpha particles are positively charged particles, and they have a large mass as compared to the electron, right? So electrons are very light particles uh, as compared to the alpha particle, so that these alpha particles are deflected backward. There should be some repulsive force exists inside the atom. That is due to what? The heavy and positively charged region. So what is the reason for the number of some number of alpha particles which retraces their original path, or the angle of deflection was 180 degree? The reason for this is what? The alpha particles are positively charged particles, right? The alpha particles are positively charged particles. So the deflection, these alpha particles are deflected back due to what? Some repulsive force. So you know that the positive repel each other, the like charges repel each other, and unlike charges are attract each other. So these alpha particles are repelled by, or repulsive force acted on these alpha particles by some other positively charged region present inside the atom, right? So Rutherford concluded that what? The entire positive charge in an atom is concentrated only in a very small region at the center of the atom, that is called as the nucleus, right? So the large angle of deflection, that is the alpha particles are deflected back because of what? There is a some positively charged core present at the center of the atom, that is called as what? The nucleus. So there is, when you can see in this animation, right, as the alpha particle reaches this positive charge, it gets repelled, right? It gets repelled. So there is a repulsive force between what? The alpha particle and the positively charged region present at the center of the atom, that is called as the nucleus, right? So in this way the Rutherford discovered the nucleus. So it is also called as what? The nuclear atomic model. Nuclear model. Then the next conclusion is what? The entire mass of the atom is concentrated in the nucleus of an atom, right? So the first one is the most of the space in an atom is empty, first conclusion. And second conclusion is what? The entire positive charge of the atom is concentrated in a very small region at the center of the atom, that is called as nucleus, second one. And the third one is what? The entire mass of the atom is concentrated, uh, the entire mass of the atom is concentrated in the nucleus of an atom. So whole mass of the atom is concentrated at the center, that is at the nucleus. So this is the third conclusion. Next one, the alpha particles which are traveling directly towards the nucleus, they directly get retraced or deflected back due to what? The repulsive force between the positively charged alpha particle and positively charged nucleus, right? The alpha particles which are traveling directly towards the center of the atom, they retraces their original path due to Coulomb force of repulsion or repulsive force between the positively charged particle, the positively charged alpha particle, and the positively charged central core present at the center of the atom. And the next conclusion is what? The negatively charged electrons, they are very light. The mass of the electrons is very small as compared to the alpha particles, so they do not affect the passage of alpha particles, right? Only the passage of alpha particles is affected due to what? The positively charged core present at the center of the atom, that is called as the nucleus, right? The negatively charged electrons do not affect the passage of alpha particles. So once again, let us see the conclusions in very short, right? The most of the space in an atom is empty. The first conclusion is the most of the space in an atom is empty, and the entire positive charge of the atom is concentrated in a very small region at the center of the atom, that is called as the nucleus. Next, the entire mass of the atom is concentrated at the nucleus of an atom, right? And there is a Coulomb force of repulsion between the alpha particles, positively charged alpha particles, and the positively charged nucleus present at the center of the atom. And the conclusion is what? The negatively charged electrons are very light and they do not affect the passage of alpha particles, right? Now, with all these discussion, we have to uh, explain the Rutherford atomic models, and we have to write the what? The postulates of Rutherford atomic model. So before going to discuss the Rutherford atomic model and its postulates, we need to define here the two definitions. One is what is impact parameter, that is the alpha particle trajectory. You know that what is meant by trajectory, that is the path followed by the alpha particle, that is called as trajectory of alpha particle. And then we have to define what is impact parameter, and one more definition is what? The distance of closest approach. So these two definitions related to the alpha particle scattering we need to define here. Then first one, what is an impact parameter, right? So we have the nucleus here, then this is the path of the alpha particle, right? So when this alpha particle reaches near the nucleus, due to the repulsion, alpha particle is positively charged, so nucleus is positive charge, so there is a deflection in their path takes place, right? When the alpha particle reaches directly towards the center, towards the nucleus, it retraces its original path. But those particles which are away from the nucleus, right? So angle is very small, scattering angle is what? The very small, you can observe here, right? So now what is an impact parameter? Impact parameter B, it is denoted by the symbol B. It is the perpendicular distance of the initial velocity vector of the alpha particle from the center of the nucleus. So this is the initial direction of the alpha particle, right? Then when it reaches the when it comes near the nucleus, it's get deflected or scattered. Now the impact parameter is a distance, right? It is a distance. Which distance it is? Distance from the center of the nucleus to the direction of the alpha particle. So this is the direction of the alpha particle, this is the initial direction of the alpha particle, this is the center of the nucleus. So this distance is called as what? The impact parameter, right? So it is the perpendicular distance of initial direction of the alpha particle from the center of the nucleus, that is called as impact parameter. So this is the center of the nucleus, right? Then this is the initial direction of the alpha particle. At this position it gets deflected, but initial direction is this one only. Now the impact parameter is what? This distance is called as what? The impact parameter. The perpendicular distance from the initial direction of the alpha particle from the center of the nucleus. That is called as impact parameter. And the impact parameter is given, or it is calculated by the formula B is equal to Z E square cot theta by 2 divided by 4 pi epsilon naught half m v square. Here Ze is the charge of the nucleus. You know that Z is denoted to atomic number, right? Then E is charge of the electron. So Ze is charge of the nucleus, right? Then theta is the angle of scattering. 4 pi epsilon naught, it is a constant. Epsilon naught is a constant. It is called as permittivity of free space. And half mv square, it is what? The kinetic energy of the incident alpha particles. So from this equation you can get the impact parameter. What is impact parameter? Now the second definition is what? The distance of closest approach. What is the distance of closest approach? So the minimum distance up to which an alpha particle traveling directly towards the nucleus can move before coming to rest and retracing its path is known as distance of closest approach. So you know that now alpha particle is a positively charged particle. Nucleus, that is the nucleus is also is having the positive charge. So when alpha particles comes towards the nucleus up to a certain distance, up to some minimum distance it comes. After that, due to a Coulomb force of repulsion from the between the alpha particle and the nucleus, it retraces its original path. So for example, the alpha particle reaches up to this point, then it retraces its original path. So then this distance is called as what? The distance of closest approach, right? The minimum distance up to which an alpha particle traveling towards the nucleus move before coming to rest, right? And it retraces its path is known as what? The distance of closest approach. The distance of closest approach is given by the formula R naught. R naught is equal to 1 divided by 4 pi epsilon naught. So just we have to mention the formulas here. 2z e square divided by k, right? This is the formula we are using. So distance of closest approach means what? The minimum distance up to which an alpha particle traveling towards the nucleus can move before coming to rest, right? And then it retraces its original path. So there is a repulsion between what? The alpha particle and the nucleus. Up to a certain distance it goes towards the nucleus. After that it comes back. So that minimum distance it can travel from the nucleus, that is called as what? The the distance of closest approach. For example, up to this point an alpha particle can reach. After this it retraces its original path. Then the distance of the distance up to point at which it reaches from the nucleus, that is called as what? The distance of closest approach, right? And where this distance of closest approach gives an idea about what? The size of the nucleus. So size of the nucleus is of the order of 10 to the power minus 15 meter, that is 1 Fermi, and size of the atom is of the order of 10 to the power minus 10 meter. So in this way we can, from the distance of closest approach, we can get the idea of size of the nucleus also, right? And you can calculate this by the formula R naught divided by R naught is equal to 1 divided by 4 pi epsilon naught 2 Ze square. Again Ze is the charge of the nucleus and K is kinetic energy of the alpha particle, right? So with all this discussion with all this discussion of the what? The different atomic models, right? Then alpha particle scattering experiment, its observations and conclusions, right? And the two definitions, what is distance of closest approach and what is impact parameter. With all this discussion will end the video class here. We'll discuss the next point, that is the Rutherford atomic model and its postulates and merits and demerits in the next video class. Okay, thank you students.